welcome to True Projects. In this video, we are going to explain about database receding horizon control of linear network systems. Introduction. The project focuses on the application of data-driven methodologies in control theory to network systems with linear dynamics. These systems are difficult to model from the ground up because parameter identification is either unfeasible or prohibitively expensive. Because the system is decentralized, agents can only access information that can be measured locally and must communicate with one another to forecast network responses and decide on control actions. To stabilize the network system characterized by linear dynamics, the project provides a distributed database predictive control technique. Objective. This project's goal is to offer a distributed database predictive control technique for stabilizing a network system represented by linear dynamics. The proposed methods enables agents to collaborate to forecast future system evaluation without prior knowledge of the dynamics. Instead, relying on learning a database representation from a single sample trajectory, the linear quadratic regulator issue with a finite horizon is restated as a network optimization with separable objective functions and locally expressible constraints. The resulting controller is stable and has been confirmed using numerical simulations. Requirements. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system Windows only, processor i5 and above, RAM 4GB and above, hard disk 20GB and above. In software requirements, we have Python IDEL with 3.7 version. Methodology. To implement this project, we have designed the following modules. The first module is Network System Formation Phase. This is the initial step where the network structure is defined. It involves identifying the nodes in the network, understanding the interconnections, and determining the dynamics of each node. The network can be represented as a graph where nodes represent individual subsystems and edges represent the interactions between these subsystems. Second module is Initialize Network with Actuator Nodes. In this module, the network is equipped with actuator nodes. Actuator nodes are the components responsible for controlling the individual subsystems. They take input signals from the controller and apply appropriate actions to influence the dynamics of the respective subsystems. The selection of the actuator nodes is crucial as it directly affects the control strategy and system performance. Third module is Optimize Network. After initializing the network with actuator nodes, the control strategy needs to be optimized to achieve the desired system behavior. The optimization process involves selecting appropriate control parameters, tuning the controller gains, and designing the objective function that reflects the desired system behavior and performance metrics. Fourth module is Optimization Graph. The optimization graph is a fundamental component of database receding horizon control. It is a data-driven model that captures the system dynamics and interactions between nodes in the network. The graph is continuously updated with new data from the network, ensuring that the control strategy adapts to the changing system conditions and remains effective over time. Execution. For the execution of the project, we need to open the code folder. This is the code folder. This is main code file. This is run.bat file. Instead of executing our project in the command line interface, we have created Windows batch file to execute the project. Double click on run.bat file. This is the graphical user interface which we have created using Tkinter library in Python. Using this GUI, we will interact with the project. Click on Network System Formation Phase to generate graph with simulation nodes. In above screen, each red color is the node in the network graph and blue color is the base station. Now click on Initialize Network with Actuator Nodes button to allow each node to read distributed data from neighbors, and then choose Actuator node which is closer to the base station. In above screen, green color nodes are the actuator nodes and the nodes in the big circle are neighbors to one another. In text area, we can see the names of selected actuator nodes. Now from Node ID drop-down box, select any node to send data in network by optimizing path selection. So here I am selecting 3 and now click on Optimize Network. So this line represents the transmission data. So here we can see that node 7 selected its nearest neighbor and transferred the data to its nearest neighbor. So we can see that node 7 transferred the data to A13, which is a actuator node, and from A13 the data is transferred to the base station. In this way the data is transferred from the source node to the base station passing the actuator node. So we will select another ID from the node ID. I'm selecting 7 and click on optimize network. So here we can see this is the path from which the data is transferred from the source node to the base station. So node 7 selected its nearest neighbor, which is node 16, and from node 16 the data is transferred to the actuator node, which is A319, and from this actuator node the data is transferred to the base station. In this way the data will be transferred to the base station. Now click on optimization graph. So here we can see that x-axis represents the technique name and y-axis represents the resource consumption. In above graph, red line represents resource consumption for unoptimized technique and blue line represents resource consumption for optimized technique. So by applying optimization, we can save resources. Close the graph, exit the GUI, and the final conclusion of the project is the suggested distributed database predictive controller is effective in stabilizing network linear dynamics characterized by unknown system matrices according to the project's conclusion. The method enables agents to learn a non-parametric representation based on a single trajectory and use it to create a controller as the answer to network optimization problem that is tackled in a receding horizon and distributed manner. Future work will concentrate on quantifying the tolerance in terms of available data, constructing a terminal cost without knowledge of the underlying model to ensure stability when the stabilizing terminal constraint is omitted, extending the results to cases where the state and input are constrained, characterizing the robustness properties of the introduced control scheme, improving its scalability, and considering more general scenarios including the present.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.